So hello and welcome everyone. My name is Jay Dalsaniya and in this video we are going to solve the problem root to leaf path sum. So this question is quite easy. So without any delay, let's try to understand what the problem is saying. So in this question you will be given a binary tree and an integer s. Check whether there is a root to leaf path whose sum is equal to s. Okay, fine. So basically in this question you will be given a binary tree. Okay, fine. So let's say binary tree is something like this. Just an example, I'm taking just an example. So let's take 1, let's take 9, let's take 4, 5, 2 and 3. Okay, and they will be giving you a sum variable that will be equivalent to, let's say in this scenario it will be equal to 6. So you have to find out that if there is a path from root to any of the leaf, from root to any of the leaf whose sum is equivalent to 6. So here I can observe from root to leaf, this is the path whose sum is equivalent to 6. So there is one more path available from root to leaf, that is this path, and its sum is equivalent to what? 15. And there is one more possibility. So this is the another path available, and its sum is equivalent to what? This is equivalent to what? 14. Okay, so you have to find out for the given value of sum whether a path exists from root to leaf whose sum is equivalent to given variable. So that's the question. And if yes, then your output will be saying 1, and if the output is not there, then it will be saying 0 in the output. Okay, so that's the question. Now here if we try to think what we can do over here is that, let's take one example. I like to explain something. 5 and 6. Okay, so in this example number 2, let's take example number 2, and here let's say the sum variable is equivalent to 6. So here what you can do, you can use a simple traversal on the given binary tree, and whenever you reach a leaf node, at that time you can just check the variable sum. Okay, fine. So that means whenever I am going on the left hand side or I am going on the right hand side, I have to reduce the value of sum. Yes, absolutely, that's what you are supposed to do. Let's say the value of sum over here is equivalent to what? 6. Let me just change the color. Okay, so we can understand the difference. So let's say sum is equivalent to 6 over here. Now when I move in this direction, what I will do, I'll decrease the sum by the root value. So sum will be equivalent to what? 5. 6 minus 1 is 5. Now again, when I move in this direction, now my sum will be 5 minus 2 is equivalent to 3. And when I reach this leaf node, I will just check the sum and I will subtract the value of the leaf node from the sum. And I will check, is sum now equivalent to 0? Yes. So what we will be doing in this scenario? In this scenario, this 3 will be returning true to its parent, and this 2 will be returning true to its parent. So this 1 got true from the left hand side. Similarly, it will be doing the traversal on the right hand side as well. So 1 will be making a call to this 4. So here when this recursive call is made, sum will be equivalent to what? 6 minus 1, that will be 5. Now again it will make a call to this one. So here what will be the sum? Sum will be equivalent to 5 minus 4, that is 1. And here when it makes a call, sum will be 1 minus 5. So sum comes out to be what? Minus 4. And at this position I will do subtraction of the leaf from my sum. Minus 4 minus 6. So I got to know it is minus 10. Okay. So whenever at any leaf point your sum is equivalent to 0, that means yes, the path is possible and you are supposed to return, in that scenario you are supposed to return what? True, right? Okay, so basically now what will happen in this scenario? So this 6 basically is not equivalent to what? 0, right? It is not equivalent to 0. So what it will do, it will return a false. Now 5, from the left hand side there is nothing present, there is a null present. So what I will do, for null nodes I will be returning false. For null nodes I will be returning false, and there is a reason behind it. I will explain. So the reason is that for the nodes that are null, for null nodes I have to return false, that no, the answer is not possible. So this is what I am going to do for null nodes. Okay, now 5 got false from the left hand side and right hand side, so overall they will do logical OR of it, so it will be an overall false. So 4 will also return false over here, and this one will be getting false from the right hand side. So here it got two responses, one true and one false. So I'll take the logical OR of it, and the overall output comes out to be true. Yes, the sum 6 is possible for a path from root to leaf. So that is what I'm going to do. Now I have told you that I am returning basically false for the null nodes. Okay, so what is the reason behind it? So let me give you an example in which the sum is not possible. Let's take sum equals to 1000, or let's take no, not an hypothetical number. Let's take sum equals to 5. Now pay attention to this binary tree. So here it is 4, here it is, let's say 3. Okay, fine. So what will happen? Let's do, so sum equals to 5. So currently over here, what will be the sum? Sum will be 5. Now I will make a call on this side. Okay, I made a call over here, but I know that on the left hand side I don't have any node. I have null nodes, right? So I'll not make a call over here. I will not make a call over here. Or let's say if I make a call, then this null will be returning what? False. So I am saying that what is the reason behind returning a false? Okay, so now 1 will be making a call to 4. So sum over here will be what? 5 minus 1, that will be 4. Now let's say this 4 basically makes a call to the left hand side. So here what will happen? So here when it makes a call to the left hand side, sum will be what? Equal to 0, because this 4 will be subtracted from this sum and I'll be getting 0. So here you can see for this null node, I got the sum to be what? 0. So here if you return true, then that means there is a path from root to leaf whose sum is equivalent to 5. But that is not absolutely true, right? This is not a path from root to leaf. This is a path from one of the root to one of the node, right? It is not sum of the path from root to leaf. The question says sum of the path from root to leaf. That's the reason we are not going to return in this scenario true. Okay, so in case of null nodes, even though your sum equals to 0, I'm going to return false. So this will be returning false. Now here when it makes a call, 4 makes a call to this 3, your sum will be equivalent to what? 1. And now if you again subtract the sum, so sum 1 minus 3, that will be equivalent to minus 2. Okay, and overall this will be returning what? False over here, and this 4 will be returning overall false, and this output 1 will be returning false. Okay, so that's pretty easy. So now let's try to see what is the algorithm over here. So algorithm is pretty simple. So let's say we will be writing a function, and let's see what function the question is given. It is has path sum. Let's see, has path sum has quite a unique name, has path sum. And now let's say I will be passing a root node and I will be passing some sum like this. So I said whenever I reach a null node, if the root is equivalent to null, what I will be doing? I will be returning false in this scenario. That output is not possible. Okay, fine. Now I will only check when I execute a leaf node, when I am standing at leaf position. So I'll check if root dot left is equivalent to null and root dot right is equivalent to null. So this indicates a leaf node. So in this scenario, what I will do, I'll try to subtract this sum. So I'll say s minus root dot data, that is leaf dot data. If this is equivalent to what? 0. So in this scenario, what I will be doing? I will be returning what? True. And else what I will be doing? I'll be returning false. For leaf path, for this path, sum is not now, sum is not equal to 0. Okay, and then I'll be making a recursive call has path sum. I'll be doing root dot left and I'll be subtracting the sum root dot data from the sum. And here pay attention, I am doing logical OR. Okay, any one of the condition has to be true. Has path sum, and here root dot right, and here also s minus root dot data, and here the function ends, end of the function. Okay, so this is our entire code, and if you pay attention in this code, what is the time complexity? Here the time complexity is what? Order of n, because here at least you will be traversing all the nodes. Okay, fine, and none of the node will be traversed more than once. And what about the height? So obviously if you draw a binary tree, in a binary tree if you traverse all the nodes, then the height will be then the height of this tree will be equivalent to what? Log of n if there are n number of nodes, and the recursive stack will be utilizing the space equivalent to height of the tree. So the space complexity comes out to be order of log n in this scenario. So this is our time and space complexity for the given question. Okay, so now let's try to write down the code for the same. So if my root is equivalent to null, I will be returning what? False. And now let's say if I have a leaf node. So if my root dot left is equivalent to null and root dot right is equivalent to null. So this is a leaf node. So I'll subtract the root data from this sum, and after subtraction, if it is equivalent to 0, I'll be returning what? True. Else I will be returning false in this scenario. Okay. In other case, I will be making a call to the left subtree and the right subtree, and I'll be subtracting the root data from it, and logical OR has path sum, and here root dot write s minus root dot data. Okay, and this will be returning whatever is the value. Okay, now let's say to a compiler and let's see if we have made any compilation errors or not. Okay, so the code is working perfectly fine, and let's try to submit and let's try to see. And we can see that the problem has been successfully submitted. So if you really enjoyed this video, then do hit the like button and share down your approach in the comment section below. So thank you for watching. I will be seeing you in the next video. Till then, keep coding.